So today we would like to talk to you about this specific topic, fighting cancer with VMware technology, GPUs and machine learning. So let's make sure that everybody has seen this disclaimer, and let's go over a really short agenda that we have. We'll do a quick intro, we'll skip right through to the technical bit, which is the GPU, why use a GPU with machine learning, artificial intelligence. How do we support GPU and how do we expose those devices to the workloads? And then Johan will take over and talk a little bit about a really cool customer case that he did. So you might have seen the keynote yesterday.
Who has seen the keynote yesterday? Who saw the last 3 minutes of the keynote?
Yeah,
awesome. We're going to dive into that specific use case and show what we actually did there. So it's really awesome.
Exactly. And we'll try to leave some time for Q&A at the end of the session. So if you have any questions, please wait until the end of the session. So as a short introduction, I'm Niels Hagoort. I'm based in the Netherlands. I'm a VCDX. I work for VMware as a technical marketing architect. And I cover basically everything that touches ESXi. So that's resource management, that's hardware compatibility, that's hardware accelerations, etc., etc. I am the co-author of the Host Resources Deep Dive book and the Clustering Deep Dive book with fellow Dutchies Frank and Duncan. And Johan, please go ahead and introduce yourself.
Yeah, my name is Johan from Amersfoort. I'm an EUC architect or tech marketing architect at ITQ. I focus on everything that has to do with end-user computing. And since the last year, I've been focusing on somewhat more on machine learning, deep learning on vSphere as well. I authored the VDI design guide. And there's an intentional reason why both myself and Niels are blurred here. So by show of hands, who is 100% sure that the person on the right is me and the person on the left is Niels? Who isn't sure? Who is like 95% sure?
96.
96? Okay. Yeah. Good to know. And we'll dive into that later on. So let's talk about GPUs first. Why a GPU? So this was the actual first GPU that was ever created. Back then it wasn't called a GPU, it was called a video display controller. And it was built by Fujitsu. And this video display controller was able to produce 4 colors with 16 KB of RAM, and it has some awesome performance. If you look at this game, this was the actual first game that was powered by that GPU, which is Gunman. Look at the frame rate. That's awesome, right? No latency. Well, you get the point. We jump ahead a couple of years. And to me, this was the actual first iconic GPU. Who recognizes this GPU? Which one is it? Which one?
There we go.
Monster 1, indeed. This is the Diamond Monster 3D Voodoo 1. And this was the actual first GPU built for a specific purpose. That purpose being to talk to an API, which is the Glide API, and render really specific textures within a game. To give you somewhat more overview, this is which game? Nope, Quake. Quake 2. And this game is software rendered. What you can see is that the textures are a bit blurry, the ground here is a bit blurry. Now, insert a Voodoo card in your system and suddenly stuff becomes smooth. See the difference? Is that awesome or what? Who played Quake with that card? The real thing here is that although it looks a bit different, it looks a bit better, but the true thing that you achieve here is a lower latency. And who plays first-person shooters knows that latency is the one thing that gets you killed or gets you to kill someone else. And this card reduced the latency in such a
Way?
Yeah, such a way.
I don't know.
I enjoyed my parties last night as well. Still have a tiny hangover, but that's more due to the fact that Ajax didn't win last night, and they're supposed to. But yeah, latency. Latency is key in games. Now, let's jump ahead 20 years in time. Same game, different card. So NVIDIA introduced the Turing architecture earlier this year, and with that architecture that includes a technology called real-time ray tracing, you're able to again offload specific calculations to the card, and in this case the CPU the CPU intensity and the CPU usage is lowered by offloading, in this case, specific lighting textures to the card. So again, reduced the latency, it reduced the CPU usage, and your gameplay is a lot better. Now let's look at how we use GPUs in our modern life. By the way, Quake 2 RTX is free to download in Steam. So if you would like to, you can play that iconic game, but with the whole new user experience. It's really awesome. We don't have a demo, unfortunately. So let's look at GPUs in our daily life. So probably everyone here has either a MacBook or a Windows laptop, and it does contain a GPU. It could either be like an integrated GPU or a dedicated GPU, but that GPU mainly is used for displaying graphics, right? But we have more devices. Our phone, for instance, a smartphone has a GPU. And in most cases, it's used to display graphics. But what it also does is, for instance, if you use Siri or Google Assistant, it translates or it uses the voice recognition in your phone to convert text to speech to text, or speech to specific tasks in your phone. So if I ask Siri to call someone, it'll use my voice to do that, and it uses the GPU to do that processing of AI in this case. Same thing with your smartwatch. Talk to your smartwatch, say you should call someone, and it'll do that. And it'll use the GPU both to display what's happening there, but also to calculate or to process that specific task. Raspberry Pi, same thing, has a GPU. In this case to mostly encode a video stream, but again, it has a GPU to do so. A car, in this case a Volvo, but any other like modern car also has a GPU, again to display the video output. But my car has a alarming system that if I, for instance, approach a crossing, someone is coming from the right or from the left, I hardly notice that person because I probably have the same issue as I have right now, little hangover. The car will warn me that that person will pass by, and if I ignore the warning, it'll brake. It uses the GPU to process that. So again, another example, perfect example of how to use a GPU in our daily lives. And the last one is a personal thing. I bought a Synology 918 quite recently. It has a GPU, but the thing is that this is the first device I saw or I own that has a GPU without a display output. So the only reason this device has a GPU is to perform a certain calculation or to encode video streams. Right. Let's look at GPUs in the data center, right?
Yep. Thank you. So like Johan said, we see GPUs popping up in each and every data center in the enterprise, right? And that's not only about VDI and virtual desktops, that's also about doing computations on those GPUs. So we see a lot of traction with GPUs in HPC platforms, right? All about machine learning, artificial intelligence. And this is why we need general purpose GPUs, GPGPUs, is because they bring us a high degree of parallelism. And we'll dig a little bit in what that actually means. But first, let's look at why we need a GPU, because we already have CPUs in our packages, in our hosts, right? And the question you want to ask yourself is, do I need the lowest possible latency, or do I need high throughput? So if we look at a CPU, a really high overview, the first thing that we notice is the amount of cores within a CPU package. Now, depending on make and model, this probably around 28, 32, or even higher core count now with new AMD EPYC processors. When we see a GPU, and we are talking about a lot of cores in one PCIe device, right? So looking at the current flagship offering with NVIDIA, the Tesla V100, we are talking in the excess of 5,000 cores on one PCIe device. But the latency versus throughput is not only about the amount of cores. Looking at a CPU and a really high overview of a CPU architecture, again depending on make and model, we see a lot of cores on a CPU package, and we see the whole memory construct set up for the data to reside as close as possible to the core for doing computations, because a CPU does computations in a serialized way. So it needs its data as close by to obtain that lowest possible latency for computations. So we see a level 1 data cache on each and every core, a level 2 data cache, which can be in the excess of multiple megabytes already today. And this is all core dedicated. Now, whenever data is not residing in those levels, it'll reach out to the level 3 or last level cache. And if data is not residing on that layer as well, it'll reach out, call out the system agent memory controller and go to the global memory. So everything that makes sure that the data is as close as possible. Now, when we look at a GPU architecture, again, depending on make and model, but this is a high overview of a GPU device, we see sort of the same memory constructs. So we have a level 1 data cache which is shared amongst various cores. We see a shared a level 2 cache which is shared amongst the whole device. And you see that whenever screen buffer is assigned in GDDR5 memory, or perhaps GDDR6 memory today in newer cards, the whole architecture is somewhat tolerant of memory latency. And that is because we need to keep the GPU busy, sort of to mask that memory latency, right? And we're still talking microseconds here, but still. So whenever we are scheduling against a CPU, we do that on a per core basis. Obviously we can use hyperthreads or SMTs as well. But with GPUs, we are scheduling against processor clusters that contain multiple streaming multiprocessors that contain a lot of cores. So now you are scheduling your machine learning workload against a lot of cores at once. That's parallelism, that's high throughput for you, right? So it's good to understand that the main differences between the CPU and the GPU architecture. Now let's talk a little bit on why that is important with machine learning. So let's go firstly over some CPU or machine learning terminology. So we see CUDA, which is developed by NVIDIA, which is a framework for computational workloads on GPU. We see TensorFlow, that's a term you see a lot these days, developed by Google, and you can extend that with CUDA extensions if you want. And we see OpenCL, the open computing language. Now, whenever we look at machine learning and deep learning networks and workloads, this is basically what happens. So neural networks, like we see here, are a component of machine learning. And on the left-hand side, we see some input values, the x's. On the right-hand side, we see some y's, which is the output. Now, in each and every neural network node, which are the blue dots basically, and those can be like in the excess of thousands or millions even, a lot of computation is going on within each neural network node. And this is an example of what is happening, right? So again, we see the x's, we see the weight values, the w's, we see a sum identified by the sigma symbol, and an activation function is applied to that, giving it non-linearity in a neural network. And in the end, we'll have some output. In the end, yeah, well, basically, this is math going way beyond my pay grade. But to give you an idea that this is happening in each and every neural network node, right? So a lot of computations done at once. And this is exactly why we need GPU, because we now have thousands of cores doing computations on this level. So to make it a little bit more clear to you what this actually means, we have this image recognition example for you, which is a TensorRT workflow. And basically what we see, this is running on a Skylake, Intel Skylake CPU, and you see that we have an images per second on the lower left side of around 4, right? It's working, but it's not performing that great.
It's a lot faster than Greg Lavender's demo this morning. He was able to process like 0.8 dog per second.
Okay, so well, there we go.
Yeah.
Well, 4 is actually quite good. When you compare that to a GPU, for instance, you see a lot of parallelism going on, and we hit almost 900 images per second, right?
On a single card, on a single GPU.
On a single GPU, and you can even expose multiple GPUs to one workload if you want. So let's dig a little bit deeper into exactly that. How we support GPUs with vSphere. How do you expose those capabilities to workloads? Now we have multiple options here. So whenever you need to have a full GPU dedicated to one virtual machine, to one workload, we can do that. And we can do that with direct path I/O or with NVIDIA vGPU. We can also have, if your data scientist, for example, needs a lot of processing power, we can even have multiple GPU devices assigned to one single VM. And we can do that with direct path I/O again, with BitFusion, FlexDirect, and NVIDIA vGPU. Now the last option is basically what we did with compute resources as well, right, with ESXi. Carve up memory and CPU resources and divide them over multiple VMs. We can do the same thing with GPUs, with integration with FlexDirect again and with NVIDIA vGPU. So let's dig a little bit deeper in all these options we just explained. First of all, direct path I/O. Now by show of hands, who is using direct path I/O? I have 1, 2, 3, nice. And basically what we see and what we hear from customers is the main reason why we do not want to use direct path I/O is that it comes with a lot of constraints on the vSphere features, right? So you don't have portability with vMotion, HA is not supported, you name it. Then direct path I/O basically makes sure that the PCIe device and the hardware address of that specific PCIe device is mapped to the virtual machine and the guest running inside the virtual machine. So you are basically not able to move that VM, live migrate that VM to another host. So this is something that we are thinking about doing. This is a technology preview, and in future releases of vSphere, we are looking at doing exactly this, capability mapping of a PCIe device and expose the capability to the virtual machine. So no longer do we map the hardware address of a PCIe device to the virtual machine, we will expose a capability. Capability meaning that we can now assign a virtual machine with the type of GPU, right? And maybe even a specific model, a V100 for example. And now DRS has that intelligence of making sure that it places that virtual machine on a host that has that exact same type. So if you look at the left-hand side, this is where we are today. If you use direct path I/O, you'll have a lot of manual configuration, right? And you constrain yourself for initial placement. So with hardware acceleration aware DRS, you can now basically expose that, like we said, that capability to the virtual machine, and DRS will take care of the rest. Obviously, you would need hosts that are equipped with a GPU, and that GPU still needs to be available, but it's a step in the right direction, if you ask me. Second, we have BitFusion FlexDirect. So BitFusion is an acquisition we did recently, and it is a really cool technology. This is all about making sure that you are as flexible as possible with the usage of GPUs in your enterprise data center. So what we have on the lower side, we have ESXi hosts that are equipped with a GPU device, or multiple even, or an FPGA for that matter. And on the top side, we have ESXi hosts running client VMs that don't have a GPU, but we still want to execute machine learning jobs in those client VMs. And we can basically remote the CUDA instructions or OpenCL instructions from the client VM over the fabric to a BitFusion server VM that is equipped with a GPU. Now over a fabric means that you can just use your TCP/IP network, right? Depending on what the workload exactly is. You could also opt for RDMA, for example, to have even lower latency. But let me emphasize that this is not about graphic acceleration. This is not for VDI, for example. This is strictly for machine learning workloads, because basically you're firing up the machine learning workload to the server VM and you expect the results back, right? So I have this short demo that we have set up, just to give you a little bit of a taste what BitFusion actually is. So we have some CentOS virtual machines that are running a machine learning workload, but those are hosted on a host without GPU. And we have this really beefy host that contains 4 GPUs. And that is running the server VM for BitFusion FlexDirect. So whenever we open the client VMs and execute a machine learning workload, you will see, and we'll assign some GPUs to those workloads as well. So we have 2 examples. On the right hand side, we'll assign 1 GPU. On the left hand side, we'll assign 2 GPUs, and we'll have different models, training models for the machine learning algorithm. So whenever we execute that command, we fail because TensorFlow expects a GPU, obviously. So we can remedy that with BitFusion FlexDirect because we can now execute the same command, but make sure that we redirect the CUDA instructions to the server VM. So we'll put FlexDirect the command just before the machine learning workload, and the N2 or N1 in this specific case is all about the number of GPUs that you want to assign to the certain workload. Okay? So now you will see that it successfully executes on both examples. And whenever we look at the BitFusion FlexDirect UI, we see that the server VM has 4 GPUs, of which 3 are now assigned to the client VMs. So we have 2 GPUs running for one workload and 1 GPU for the other one. And when we skip back to the examples, we see that everything is being processed on the server VM, and everything goes like the GPU is actually local to that machine. Pretty awesome technology, if you ask me. So this is all happening, again, like I said, over the fabric, and depending on what the actual workload is, latency-wise, it shouldn't really matter to do it over a fabric. So we see the whole workload going on and executing 70%, 80%. And the beauty of this is once the workloads are done for the client VMs, it'll actually release the GPU again. So now you can use the GPUs for other machine learning workloads. So giving you a real flexible solution in utilizing those GPUs. And you can assign, like we did in this specific case, a full GPU, but we can also assign partial GPUs for specific workloads. So really cool tech. Like I said, it is a acquisition that we did recently, and we're looking to integrate this in the vSphere solution pretty soon. Let's head over to the last option to discuss, which is NVIDIA vGPU. Now we have a strong partnership with NVIDIA, and we both co-developed this exact model, which is you have a host server with a GPU that is obviously NVIDIA supported, so an NVIDIA GPU, and you will actually need to install a kernel module on the ESXi layer, okay? So a VIP module, and that introduces a different layer of scheduling, and that scheduling is all about how many cores, how many screen buffer do I divide over multiple VMs, right? You would also need a CUDA and driver in the guest OS itself, so the whole stack end-to-end knows that it's now utilizing NVIDIA vGPU. Pretty cool technology. And as of 6.7, we co-developed some portability for VMs that are equipped with a vGPU. So we had the option to suspend and resume. So suspend on the source host, move that virtual machine to a destination host and resume. In 6.7 update 1, we introduced vMotion support even for vGPU enabled VMs. But this still came with a, well, sort of noticeable stun time, right? That could be, depending on whatever the workload is, could be several seconds. It's good to know that in 6.7 update 3, we greatly enhanced that performance for vGPU vMotion support. So, talking about 6.7 on all the update releases, whenever you want to utilize GPUs in your data center, make sure that you are running the latest version of vSphere, because update releases aren't anymore about bug fixes or patches. It's bringing new capabilities with each and every update. So like we said, we had suspend and resume as of 6.7, vMotion support in update 1, and update 3, the enhanced vMotion performance, and multiple vGPU support for one virtual machine. Talking about vMotion, I think Johan has set up pretty sweet
a
vMotion demo.
So who still remembers the first time you saw like vMotion, the original version of vMotion?
Compute vMotion.
Compute vMotion. Was that awesome or what? That was cool, right? Who's never seen a vMotion with a VM that has a GPU enabled?
Okay.
A lot of hands. That's good.
Thanks.
Okay. Let's recreate that whole vMotion memory again. Right. So we have a button here. Wow. Okay. So what you see here is a virtual desktop. It has Quake RTX installed, but we won't be playing that. You can see here a community tool called RD Analyzer. You can see that I'm connected over Blast. Oh, you could see that. And on a vGPU enabled machine. The machine I'm logged into is called YOLO. There it is. And it has 6 CPUs. It's connected, or it's running on ESXi 2. And it has a Grid T4 8Q profile connected. So that's a Turing card with 8 gigs of frame buffer. At the left, or at your left, you can see YouTube and a video of 2 really awesome guys. Who has seen these videos on our channel before? Okay, we have a Lightboard channel full of like 40, 50 videos, all containing stuff around GPUs, around CUDA with Frank Denneman, a lot of cool other stuff as well. So it's playing. We execute the migration, and this is based on ESXi 6.7 update 2. So the stun is still there. We select a different host, which is ESXi 3. I get a warning that a GPU profile must be available. And when I finish, the actual vMotion will be executed. So it's trying to relocate it. Look at the video. You will see a short stun in a couple of seconds. There it is. And after a couple of seconds, it should automatically play again. There it is.
Yeah. So let's make sure that you use update 3 to enhance this performance.
Yeah, and please remember, this is a 8Q profile, so that's 8 gigs of frame buffer that's running on a machine with a card that has DDR6 memory, really fast memory, and you're transferring all of those changing blocks in memory through a piece of copper to another host that has the same card. And to sync those pages between cards, that's a difficult task. And I'm using 10 gigs between those hosts, 10 gigs normal Ethernet. Remember, if you're using Mellanox, for instance, RDMA, low latency connectivity, that stun would probably be even less. So take that into account when looking at this. So now it is time to dig into the customer case. Yes, might contain another demo, will contain another demo. Right, so I've been working with a customer with the Dutch Cancer Institute for the last 14 months. And I came in as an architect to design a Workspace ONE environment, based basically on the Workspace ONE suite from the cloud, but also a VDI platform. And this customer is all about innovation. They have been working with innovative technologies for the last 30 years already. They were one of the first to use specific microscopes, for instance, that were really enhanced back then. And nowadays they have the most the most innovative microscopes again, and other technologies to work on cancer research. So 30 years ago, they have a lot of data scientists working at the customer. And 30 years ago, data scientists would probably be like angry men with beards, processing giant piles of data. And back then, they probably did that on agent CPUs like this one. Who recognizes the CPU? Who worked with this CPU? No one? It's an Intel C4004, and this was the actual first CPU that had the first basis of the modern x86 architecture. So every CPU that came after it was based on this from an architecture perspective. And nowadays, they do it on massive supercomputers like this. Who recognizes this supercomputer? Right, it's the Mare Nostrum 4, located in this city of Barcelona, and it's awesome because of two main reasons. One, the first being it's built in a church. The second being that it is perfectly OCD compliant. So you can see that every host has the same color of cable in the same network card, for instance, of the same length, in the same type of switch. So it's really awesome. This is a coincidence, but we are organizing a tour to this data center tonight. I think the bus stops here at 6:30 or 5:30. You'll be brought back just before VMworld Fest. We still have like 5 spots available. It's free of charge. If anyone is interested in visiting it, just come by after the session and we'll make that work. So let's dig into the customer case again. And let's look at the last 30 years and what happened there. So if you look at the last 30 years, the number of cancer diagnoses, and this is based on the Netherlands, has doubled. And we had a massive increase in the amount of bioimaging data. If you know how easy it is to create a picture with your smartphone, and what we all do here, with this, well, almost the same ease, you could take multiple pictures of, or multiple types of data of a person being diagnosed with cancer through microscopes, through MRI images, through radiology, you name it. Because everything is digital, it's so easy to get data. And because of optics, but also because of the details and the size of sensors, we can see that every image you take or every bit of data you take has so high, a higher detail compared to 30 years ago, that the individual size of every thing you do, every image you take, increased as well. And this is a challenge. So how does that impact bioimaging? And we showed this picture, right, at the beginning. And not everyone was 100% sure. So that's again, a really good thing to know. So who has ever experienced taking a picture with either your smartphone or camera that was blurred? Okay. If you haven't, then you're probably in the wrong audience, and you should, attend photography conferences or something like that. But, right, so let's dig into that. That was me, that was Niels, right? Well, what if you have, if you took a picture like that and you have more objects, so instead of two like massive 6'4" objects that were standing still, probably because they were drunk the night before as well. That was last year, right? Uh-huh. Yeah. So you have more objects, maybe even like 52 of them. They're 20 nanometers in size. To give you an idea, 20 nanometers is 1/50,000th of a single millimeter. So it's really tiny. And those objects are constantly moving. So cells, this is a picture of multiple cancer cells. Those cells don't sit still. They're constantly moving underneath the microscope. And you have a tiny focal length. If I take a picture with my iPhone right now, you'll probably all be in focus and sharp and look awesome. But the focal length of a microscope is so small that it's hard to have a in-focus image of all of those cells. And a cell isn't a 2D object like we were in the picture. A cell it has layers. And what we do with a microscope is create multiple layers of that same cell. In this case, in the example I'll show later on, we have plus 50 cells, or 50 layers, Z-axis layers on top of each other. And the goal here is not to run some kind of image optimization framework or some kind of Instagram filter and suddenly the cells look awesome. No, the goal here for a data scientist is to bring back scientific data, because that's what it's all about. Right. So what if we know the speed of the moving objects underneath, in this case, the microscope, or in this case, the two big lumps. And we also know the speed of the camera that was moving. And we know the distance between the objects. In this case, between me, Niels, and the camera. And what if we also know the shutter speed of the camera that was taking the picture? And the aperture size. The type of lens, or in case of a microscope, the type of microscope and the type of objective that was in a microscope. Then suddenly, that is not me, and that is not Niels. This whole process is what we call deconvolution. And you see here a picture, a raw image of 3 cancer cells. And these bridges are what we call protein bridges. And the type of cancer that is shown, or what we are trying to, well, the scientific data of the type of cancer that is shown here, what is important is the data of the bridges. And with the deconvolution process I will show in the next demo, we highlight that data. Right, so, demo time. And bear with me for a couple of seconds. Okay. Right. So as you can see, it is pre-recorded. Didn't want to have a risk of no network being here. Yes. So what you can see here is a solution called Huygens Remote Manager. It's a solution built by a Dutch firm, but I'll dig into that later on. And this solution is being used to process those images, to open up an image, to analyze the image, and to bring back that scientific data. And what you can see here is that I select an image. This is the raw image of what I showed in the previous picture. And this is the picture taken from above. And here beneath you can see all 51 layers stacked up on top of each other. We select the image. Right. And we now select a profile that is linked to the type of image. You can see that the microscope type, it's the single label there. The aperture, the type of objective, and what it uses, in this case oil. And in the next window we'll select a machine learning algorithm. You can see here the deconvolution algorithm, which is called in this case CMLE, and that is a specific machine learning algorithm for this type of microscope. And in the next window we'll skip. I can set additional adjustings to the process. And what we'll also do while checking out the job. So what you need to know is now that we started the job. At the left, you can see in a minute, you can see the output of the algorithm that's running. And at the right, you can see there are 4 processes currently loaded upon the and linked to the GPU. The above 2 are graphics related, hence the G. Not really sure if you can see it, but the lower 2 processes are computational processes, and the right one is slowly filling frame buffer. So you can see here 5 gigs, 800 gigs. It's constantly processing layers of the image in the GPU. It's a grid T4 with an 8Q profile. And what you can see here is that it's running on GPU and it's running a single iteration. Machine learning does, during a training phase, epochs that are training iterations, and the more iterations you do, the better result you can get. In this case, just because of the demo, we just run a single iteration. Main reason being that a single iteration could take some time depending on the size of the image. Right. Now, let's go back to the slides, because this will take approximately 5 minutes normally to run. Right, so I already mentioned the Huygens Remote Manager. It's built by a company called SVI. They're the global leader in microscopic image optimization, analysis, and restoration. They built a solution called Huygens that deconvolves microscopic images of all types of microscopes. And they open sourced the multi-node version of this solution called Huygens Remote Manager. It's fully optimized for CUDA framework. And if we look at why a GPU in this case, what we did is the specific image you saw, we took a crop of that, and it contains 4 cancer cells. It's 1.2 gigs in size. It has 15 Z layers, so layers stacked on top of each other. And we tested that single iteration, that single crop of the giant image on a couple of different Xeon CPUs, a Tesla P4 and a Tesla T4. And if you look at the deconvolution time, so the time a single iteration takes to process, I first ran it on my home lab, and I have a low voltage Xeon D CPU powered home lab, mainly because of wife acceptance factor, and it runs on low power. A single iteration took 130 seconds and fully utilized all my CPU cores, all of them. So my machine wasn't able to do anything else anymore. On a dual Xeon E5 2680 V2, the same process took 30 seconds, or a little bit more than 30 seconds. On a newer CPU architecture, an E5 2667 V3, it took nearly 30 seconds. But also in both cases, all of those CPU resources were fully allocated by the single VM. So no other VM was able to run on the same host again. Now, see what happens. Yeah, if we want to run it on a single Tesla P4. So this is a single GPU linked to a single VM. And the whole process takes 14.14 seconds. Now run the same process on a T4 with an 8Q profile, and it runs in 10.8 seconds. Main reason here is that a Tesla T4 has DDR6 memory, while a P4 has DDR5 memory. DDR6 is much faster, so loading of the images, processing of the images takes less time. And what's really cool here is if I run or add 6 T4s to a single system, I'm able to run the deconvolution process on that same host in, let's say, 10 seconds with, well, 3 to 6 images at a time. So that shows the real impact of what you could do if you run a system with GPUs in this case, from a computational perspective. Right, so let's look at the HRM architecture and how a user or how the customer is using it. So we have our data scientists. They take microscopic images and they store them on a central image repository. We have users, researchers, clinical users, and also data scientists. They access the HRM web server and submit a job like I did before in the web server. The web server will ask the queuing manager to schedule the job, and the queuing manager accesses the different HRM nodes that are available and link to a GPU to process the job and execute it. The result is stored in the central image repository and is presented back to the web server. So a user can access the results in the HRM web server. And if you look at the vGPU architecture for this solution, we intentionally chose Tesla T4s because they have both the capability of running virtual desktops for normal use cases on a higher scale. So it has the capability of achieving higher density, but it's also capable of running machine learning frameworks without switching from a graphics to compute mode like you should do in a Tesla M10, for instance. So we have multiple T4s in a single system. We have the vGPU scheduler on top of it, and each HRM node has direct access to the frame buffer, and GPU resources are being scheduled. Based on the equal share scheduler, and I'll cover that in the next slide. Right, so when you choose the type of GPU for the resources you're going to use, it's always good to check out what type of GPU you would require. So if your machine learning frameworks, for instance, require double precision, the Tesla V100 is the only card to do so. So that would definitely be your right way to go. But in our case, we wanted to run mixed workloads, both for VDI as well as machine learning. So we chose a Tesla T4. It's always good to look at scheduling, because a machine learning framework, if it runs, you need a certain amount of QoS to ensure that the workload is going to bring back a result that's predictable. So either using the equal share or the fixed share scheduler is your way to go. Again, and in the last version of Grid that was released quite recently, I think a month ago, it's now also possible to set the priority on a per VM basis for both the equal share and the fixed share schedulers. And what VMware released, or what NVIDIA released during VMworld in San Francisco is vCompute Server, which offers a lot of flexibility in terms of licensing, because the other licenses are based on a per VM basis. With vCompute Server, you can license a single GPU in your host and run any type of workload on that GPU from a computational perspective. So when talking flexibility, this is definitely the way to go. Right, so let's look at the result. Yes. Cool. Is it running? Yes. Right, what you can see here in a minute is that the amount of frame buffer that is linked to the computational processes will be decreasing. And what you can see here is that the algorithm is creating previews that we will show in a little bit later in the demo. It's increasing, now it's decreasing a bit. It should. Let's skip. Oh, it was paused. Yeah, there we go. Right. So it's now saving the data. And every result is, that is created is at least the same size as the original image. So the original image in this case was 1.2 gigs. The new one will be as well. So at the right you can see that the computational processes have been released by the GPU. And at the left you can see here the process ID, so the machine learning algorithm is finished as well. And it should, at the result, at the queue status in a minute, it will show that it's finished. So the job is finished. Now we'll go to the result. I think the demo has some had a party last night as well.
Yeah, I guess so.
Right, so the above one is the result of the process we just showed. And if you just pause this a bit, what you can see here is the end result. And you can see that the bridges, the protein bridges, are highlighted compared to the other image. What you can also see is that where you see here a lot of diffraction, which is the same diffraction if, who's ever like snorkeled or did diving, in scuba diving? You know that if you have a mask on your face that the water diffracts on the mask, and objects on the water, like they look like 30% bigger than they are. That's because of the diffraction. It's the same diffraction that happens over here. Because again, the cells are floating either in water or in oil, and that diffracts on top of the glass. So the process took away the diffraction and it highlights every piece of scientific data on every different layer of the image. That's what we'll show right now. So we'll go to the slicer. And here it shows every single layer of the image. And on a per layer basis, it'll show what the actual data is that it got back from the original image. And there are different types of algorithms to bring back different type of data. Another example is, for instance, you can see the 4 cells have a yellow cell core, which is also called the nucleus. And there are different types of algorithms to bring back scientific data, for instance, specifically bound to the nucleus. But in this case, we wanted to bring back the scientific data of the protein bridges, and this highlights for a data scientist the data they need to find the cause, for instance, of a type of cancer for a specific patient. And I think this concludes the demo. Yes, what's really good to know is that this process could easily take a couple of weeks for a single image. And now with using modern technologies, we could reduce that to maybe minutes, or for really big 500 gig images, I don't know, 20 minutes or so for a single image. But that's really, really important to know that from a patient perspective, needing to wait until a diagnosis for a couple of weeks, that's, and unfortunately I been a patient myself. I had a melanoma, on my back, and I had to wait 2 weeks for a result coming back, which is the thing. And if we can reduce that time right now to, let's say, 10 to 20 minutes, that's awesome. So let's go to the key takeaways. vSphere and GPUs are a great support, flexible, and especially for performing workloads, and machine learning workloads, they're mandatory. Choosing the right hardware and vSphere configuration is really important. We were always, well, for the last couple of years, bringing in fixed nodes that are fully pre-configured are really awesome, but if you look at the different type of workloads you need, the different type of vSphere configuration you can make, it's always good to do host design prior to your implementation. And do a lot of proof of concepts, because upfront you can think that a certain card or a certain configuration would work, but it might also not. So take that definitely into account. And definitely check out the right vGPU settings or GPU settings in general. So before we run into questions, I think Niels would like to highlight something that he and Justin made that is really awesome.
Yeah, you just mentioned it.
Oh, right.
If you want to learn anything we talked about how to expose GPUs, why use GPUs, please head up this link. It's a learning guide. We also have an ebook for a more decision maker type of person, CIO, for example. So please go ahead and download this. And we do have some additional time, well, a couple of minutes, I guess, if there are any questions. Okay, we have 2 actually.
Oh, we have 2. Oh, yeah.
I don't know if you're doing any distributed machine learning on this platform. If you're doing distributed machine learning, do you notice a significant difference between generic Ethernet or InfiniBand, or would you say InfiniBand is still the way to go?
Wait, so let's rephrase the question because of the recording. So the question is if distributed machine learning, if there's a noticeable delay in when choosing different types of fabrics. I think the answer is yes, especially when looking at low latency connectivity like Mellanox. You can definitely see that there's a performance improvement, but it depends on the type of workload and the size of the data that you're processing. So the bigger the size of the data, the chances are that the performance increases if you have low latency fabrics. But it all depends on the data. So do proof of concepts to be sure.
Mm-hmm. We had another question in the back first. Sorry.
Yeah. Is it possible to use like the Dragon for like bioinformatics with vGPU?
Sorry, come again. I didn't catch that. We have a
There's
mic coming up.
Yeah, there's a mic.
Yeah, thank you. I was wondering if it's possible to use Dragon. It's like a bioinformatics CPU, FPGA, to use it with BitFusion, if you had any experience with that.
I do know that whenever you could utilize that with OpenCL, there should be support, but to make 100% sure, I can check out for you. We had one more question in front.
Oh, there's a mic coming over. Cool.
That's the one.
What I wanted to know, you said in between vSphere 6.7 update 1 and vSphere 6.7 update 3, the performance is improved. But what did you change that the performance is way better?
Magic. No, it's just magic.
Yeah, we basically did some magic. And it is a good question, though. Let's take that offline. We basically improved how vMotion works together with screen buffer copy algorithms with NVIDIA vGPU cards. Yeah. That's it for the time. Thank you so much for attending.
If you have any questions, please come over here.